and the Greek letters get people down, right? So this is a very concept-heavy class. It's a very Greek letter-heavy class. Those are the two things that get people down. There's not word problems. There's not algebra. So the whole alternate universe Florida thing, that's not an example of a problem you're going to have to do. It was an idea we were exploring. Can anyone tell me anything you remember from that discussion that we ended up figuring out? Is there anything you remember from that? Or did you guys are like, yes?
The bigger the number, the more even the mean will be. Not even, but more in the middle.
Okay, the bigger the sample, the more stuff is in the middle. Yes?
The mean stays constant no matter the sample
Yes.
size?
Yeah, I don't care how many groups I break you up into, there is an average age, and it's not going to change just because I took you 3 at a time versus 1 at a time, right? The way that I collect you guys, the information, will not suddenly change how old we are. I love it. And what does change as I take larger samples and plot the averages? What does change? Standard deviation gets smaller. And real quick, why does it make sense? If I go out right now and I randomly pick one person and they are 7 foot tall, that's a little like, whoa, okay, you with me? That would, 7 foot tall, you don't see it all the time. You with me? But I wouldn't go, holy shit. I would just go, oh, that's interesting. If you went and picked 30 people at random, and their average height was 7 foot, do you understand what I'm saying? Mm-hmm. Can you put yourself in that situation? You have randomly selected 30 people, and their average height is 7 foot tall. Is that something that's likely to happen? No. Is it impossible for that to happen? No. So one of two things. Either you've done something really, really unlikely, which of course can happen. That's something that humans don't understand. Just because the probability something's really low doesn't mean it never happens. Or something special is happening. There's a sports event or something, right? Where most people who play the sports are very tall. Or there's a self-help, like a convention of what do we do when people ask us how's the weather up here and shit like that, right? You guys kind of with me? So it could be an indication of there's something special happening, and that's why something really unlikely just occurred because it's become more likely. Does that make any sense? So how does that relate to this shit? Well, for individuals, I can have extreme values, extremely old, extremely young, extremely tall, extremely short. But if I take groups, it should be very unlikely to have an entire group who's made up of a bunch of extreme values. Does that make sense? So then what should happen is, if I plot all the groups, they should kind of come towards the middle. The whole thing should get skinnier. And of course, the really important thing is, it becomes more normal the bigger the samples I pick. Who remembers the number after which it becomes normal no matter what? 30. So then the book calls it approximately normal, which is true, but I call it normally enough. Number one, because I just like the way that sounds. And number two, normal enough to do what? To use the frickin' chart of answers that I gave you. Right? By the way, does everybody have the chart of answers by this time? Sounds like the Cave of Wonders and the chart of answers. Okay, everybody's got that, I guess? Okay, good. Yes, it feels like you guys are all done with my judgment. Whatever, man. Teach math, dude. Okay. This is my attempt at a concrete, small example of the Florida discussion. Florida had a very large population, right? And I was taking kind of big samples. So this one is going to have a population of 4, right? Let me get the mood lights going. So here's the problem. So I've got, this is a very old sounding problem. This sounds like chapter 3, and of course it does, because probability runs all over the damn place in statistics. I've got 4, bless you, pieces of paper with a different number, and I put them in a hat. Right? That sounds like a chapter 3 setup. Does it make sense then that of course they all are equally likely, possibility of me picking one of them, correct? So I'm assuming they're not like different pieces of paper so I can feel around for the one or whatever, right? They're all the same paper, the same weight, the same whatever. Can somebody tell me why this isn't actually uniform? What kind of distribution is a uniform distribution? It must be
One.
not, but it's gotta be continuous, yes. But if I plot the 1, 2, 3, and I make, like this is from 0.5 to 1.5, 1.5 to 2.5, it does kind of look uniform. Do you guys agree with me? Okay. The alternate universe Florida population, did it look nice at the beginning? It looked like 2 freaking potatoes or whatever, right? Just see, right? No matter what the distribution looks like, it will become normal enough after a sample size of 30. Are you with me? If the distribution starts off kind of nice already, it will take much less of a sample size to make it look roughly normal. Does that kind of make sense? In fact, if I had a distribution that was already normal, I could just pick one person. It's already freaking normal. Does that make sense? Okay. So if you have no idea what the distribution looks like and they don't say it's normal, they need to tell you it's got a sample size greater than 30. So they either have to tell you it's normal, or now they have to say the sample size is greater than 30. Is everybody with me? Okay. And just to say this again, I got to say this a few times. If I take a sample of 35 people, when I plot that, does it have to be normal?
Doesn't have to.
No, it can look like shit. So what is this 30 number then? If I take all possible samples of size 31 from any population and I plot all of their averages, that is what becomes normally distributed. Are you guys kind of with me? Do you see the distinction? So if I just take 31 people's ages and plot them, no reason it should look normal. No reason it should look normal, right? In fact, I guarantee you it wouldn't look normal. It would probably look like this, because most of you are younger, and then not many of us in here are older. You guys with me? So most college classes will look, that way. If I took from Grossman College every possible sample of size 31 and then plotted those averages, that would be approximately normal. You guys get the distinction? This is not like the most important thing in terms of doing the work, but it will. If you don't understand that, you're going to make a few mistakes in a few places. Okay. All right, I like it. Okay. Now, would you agree with me that this is actually not a bad distribution? Isn't this a nice distribution?
Yeah.
In fact, it's probably the nicest one that we've ever seen. Does it look normal?
No.
That's an obvious no, yes? Where's the highest peak? There isn't one. So is it in the middle? No, it's everywhere, right? So there's no way it's normal. Okay, so what I'm about to do, remember what we did in Florida, alternate universe Florida? I took every possible group of size 10, I think is the first thing I talked about, and I plotted those averages, correct? If you have Florida, right? Are there a lot of people in Florida? Yes, I used to be one of those people. I did my time in Florida, and they let me out, so never going back. Okay, sorry if you like Florida. We just lived there for anyway. So there's a lot of people in Florida, correct? So can you start to imagine how many groups of size 10 you could actually create? Can you understand that's a lot? Especially when you account for letting you double count people. You could pick people over and over. So every possible group of 10 would be a lot. So what I'm trying to do with this, okay. So what we did last time was very abstract, and I understand that, but I think I got a few of the key ideas across to you. This is going to be a more smaller scale, concrete, you can see shit happening example, but neither one of this or the last lecture is anything looking like what your work is going to look like. We are in the middle of understanding the idea. We're not anywhere near so before I let you out today, we're going to do a few actual concrete examples so you can see what the hell this means for you. You guys with me? Because I know that if I was in this class, I'd be like, what? Do I have to do alternate universe Michigan now? What's my homework going to look like, right? Okay. Shoot. So, looking at this, I'm going to do like a truncated version of this. can you guys agree that the mean of this is 2.5? Right? They're all equally likely, correct? None of them are heavier weighted than any of the others, so of course the average is 2.5. But just to kind of do this officially. Look at that. Beautiful exponent. Oh, sorry. So if I put this in here, so if you want to play along with me, you can. 1, 2, 3, 4. Yeah, not a 40, whatever. 4. Okay. And then I put over here the p of x, 0.25, 0.25, 0.25. Now I could do x p of x, x squared p of x, just like you guys did on the quiz, hopefully, right? You guys with me? Just to kind of truncate this, I don't know if you guys remember the shortcut. We're going to do the shortcut now. If I do stat calc, 1 var stats, but I tell it L1 and L2, right? We've done this before. This is the way they'll let you check your work on the x p of x kind of problem. The mean is 2.5. And what's the standard deviation? 1.118, right there, right? Is that cool? And again, that is the number you would get if you did x p of x, x squared p of x, the square root of the sum of x squared p of x minus the mean squared, right? You guys with me? Exactly what was on the quiz. You guys with me? Okay. All right. Now, real quick, can you guys just do this for me, just out of nowhere? Just calculate what this is for me. 1.118 divided by the square root of 2. Just take a second and calculate that for me. 0.791? Okay. Big old decimal.
Do you have any more of these papers?
This one.
Yeah.
No. This one.
That's the only one you have?
Yeah. You can have my, yeah, well, you can have the one I, oh, look. Oh, well, sure, you can have this one. The other side's got all my, oh, sorry. Yeah. All right. So remember, alternate universe Florida, I took every sample of size 10, and it was sort of a thought process, a thought experiment, right? We didn't actually go to alternate universe Florida because I don't have that technology, right? So what we're about to do now is I've got my population. This is like Florida, just much smaller, so it's much easier to work with. Are you with me? This is my population. I'm gonna pick every possible sample of size 2, which means if I reach into the bag and, what is it, a hat? A hat, okay. Reach in the hat and pick one, I can drop it back in. Are you with me? Sort of like with Florida, if I reach down and pick up a person, then how old are you? And then I drop them back, right? So if I pick a number and then I drop it back in and pick another number, tell me one thing that could lead to? What's one thing an event that could happen when I do that? I get a, yeah, sure. So I get a what? So I get like a 2 and then a 2, or I could get a 2 and then a 3, or a 1 and then a 4. Are you with me? So if you do it in a very prescribed manner, you can get all of the possibilities. Now before, you've already seen the middle of the page, but real quick, how many options are there for the first thing I pick? How many things could it be? The first thing I pick, how many things could it be? 4 things, yes? How about the second thing? How many things could it be? 4. 4 times 4 is? So I expect the complete set of everything that could happen to have 16 elements. You with me? So it makes sense that it has freaking 16 elements. So right here, I listed, so this is exactly, again, I know I keep doing this, alternate universe Florida, I took a group of 10 and I got their average, but we just talked about it. Here's the actual freaking samples, right? We can actually calculate the means instead of just talk about it. Does everybody agree? Those are all the samples you could possibly get. What's the average of the first sample there? This kicks so much ass. And we'll quickly see a pattern emerge. What's the average here? 1.5. What's the average here? 2. Do you see how this is the same? So this will be 1.5. What do you think the pattern is? You see the pattern yet? I'm just going to keep asking you guys. Do you guys see the pattern then?
It's going up.
So see how these, that's going to be 2 again? So this will be 8.5, 3, 3.5, 3.5, 3, 3.5, 4. Now again, if you just did each average, you would get those numbers, but again, a large part of math is noticing patterns so your work is quicker. So this could be like one group of people. I picked an alternate universe for Florida. It was a 2-year-old and a 4-year-old, and I averaged their ages and got 3, right? Maybe, for example. So in this picture, my data are the X's. My data are the individual pieces of paper, correct? Now my data is the means. If I plot those, that will be my sampling distribution. That'll be my distribution of means. Just like the weird pictures I drew, n equals 10, and it had that weird picture that had 2, 3 humps, one big one in the middle, right? So help me out, how many ones are there? 1 out of 16. What's 1 divided by 16? Yeah, so that's why there's a 0.0625 here. Do you see that? So I'm just constructing a relative frequency, a probability. So of course, 1.5, there's 2 of them, so it's twice as much. 2, there's 3 of them, so it's 3 times as much. 2.5, there's 4 of them, right? So 4 out of 16 is 1/4. You guys all with me where this came from?
Yeah.
So when I created this, it's because my data was 1, 2, 3, 4, but now my data is all the averages I could possibly get from every sample of size 2. That's my data, and when I plot it, I get this. Does that look more normal than it did? Obviously, yes? Is it perfectly normal? We don't know yet. We haven't gotten to the point, but it definitely looks more normal. And I think last time, correct me if I'm wrong, didn't I put up on the board the central limit theorem? I'm pretty sure I did, and the first thing was, as n gets bigger, it becomes more normal. The second thing was, the mean stays the same. The third thing was, the standard deviation changes. That was up on the board last time, okay. So the mean is still 2.5, right? So again, if we go with me, let's do this. Here we go, guys. You're like, this is all we ever do, Jack. Let's just go with you, dude. Just do your shit, okay. So just put all this data in, and put all the probabilities in. Okay, go this way. Okay, good. Okay, is that all right? Let's see. Do, yes. And then we can do our little shortcut. So again, we could do x p of x, x squared p of x. Kind of past that now, at the moment. So I can just do the shortcut, stat, calc, 1 bar stats, list 1, list 2, calculate. So the mean is still 2.5, that was the prediction. The mean will stay the same. Standard deviation, does that number look familiar at all? Where did we get that number from? From this, right? You guys with me? So every problem, let me kind of build up this. Every problem I did in chapter 6, they have to tell me it's normal. They give me a mean and a standard deviation, and when I make a z-score, I use the standard deviation they gave me, because the standard deviation they give us tells me how spread out individuals are. If I am working with groups of size 2, I need to know how spread out are groups of size 2 from each other. So one way to do that is just to freaking do this. One way I could do that is every problem I can construct this, I can do this, and I can calculate the standard deviation. I do not want to do that because this was very small, correct? Do you guys remember how I predicted how big this was going to be, 4 times 4? So what if I had 80 slips of paper instead of 4, and I picked 10 of them at a time? Sample size was 10. Are you with me? That would be 80 times 80 times 80, 10 times. It would be 80 to the 10th power. Can somebody do 80 to the 10th power? It's probably going to give it to you in scientific notation anyway, right? It's just 8 times.
3 times 10 to the 19.
Yeah, so it's like 1 followed by 19 zeros, basically. That is how big your box would be. So we'd have to like clear all the tables out, put a giant piece of paper down here and start making it. We're not gonna do that shit. I really want you guys with me on this. One way to get the standard deviation I need for when I'm working with groups instead of individuals is to do all this work for whatever the problem says. This was not a crazy amount of work, but that's 16. That's pretty good. That's a pretty good amount of work, right? And this is like the smallest it could possibly be. If I just picked 3 instead of 2, if I just used this and I picked 3 instead of 2, that would be 4 times 4 times 4. This would have 64 parts to it. Do you understand?
Lost.
What's up?
What was the 3 and the 2 coming?
3 and the 2.
Yeah, he said if he picks 3.
So how did we construct this? We had 4 pieces of paper in the hat, right?
Mhm.
And we picked 2 at a time, right? So, and that would be 4 options times 4 options, and that's why there's 16.
Oh, but if you pick 3 at a time.
If I pick 3 at a time, it'd be 4 times 4 times 4. This would be 64 big.
Yeah.
That is nothing I want to do, right? But I'm going to make you do it. No, I'm joking. The whole reason you would do this is just so you can get the freaking standard deviation. You understand? But didn't we, right? Down here, we get the standard deviation. 0.791. We got it. But didn't we get this a different way? By doing this? Where do you guys think, why do you think there's a 2 here? Because how big was each sample I picked? 2. So if I picked 3, again, if you do it this way for 3, you would have to have 64 elements, right? 111, 112, 113, 114, 121, 122, 12. Oh my God, we're still on the ones. Do you understand what I'm saying? I could do all that shit and get the standard deviation, or I could just take 1.118 divided by the square root of 3, and I know what it would be if I did all that. I really want you with me on this. Does that explain why it's divided by the square root of n? No. Can I explain that to you? Unfortunately, no, because it involves a little more math than I think most of us have. Right? And again, I have to find it, but I think I have the proof of it somewhere. There's the other thing, if somebody reminds me, if you're curious, I could post that, the proof of the uniform with the 12. Yeah, so if somebody reminds me, I could put both of those up there, and if you don't want to look at it, you just don't click on the damn thing, right? Okay. So why was chapter 6 easy? Because don't they just give us the standard deviation? I don't know if you guys have even tried to do any of chapter 6, but when I gave you the handout, that's on the other side of this, Jeff. Didn't I have to give you the mean and the standard deviation, or else you couldn't do shit?
Yeah.
All right. This standard deviation is how spread out individual times are. If I said I want to take groups of 26 gross month students, I cannot use this. I cannot use this because this only works for individuals. So if I say I took a group of 26 gross month students, what's the probability that their average time was greater than whatever? I can't use that damn thing because that is for individuals. So if we didn't know the shortcut, we'd have to construct the freaking huge thing with the yellow things and find the average, and oh my God, that would so suck. But we have the shortcut. We would take, if I wanted to pick a group of 26 gross month students, what would the standard deviation become for groups of 26? 8.63 divided by square root of 26. That's what I would get if I did all the freaking work, make the big old box like we did. But that would be an insane amount of work. Okay, maybe. Okay, so let's do this. I'm sorry. That's enough of this. I'm sorry. Let's do a concrete problem and show you exactly what you're going to do, all right? You're not going to be doing this. This was all my attempt to explain why we do what we do. So let's try some problems. So let's do this. Everybody got their Z-score charts?
Yeah.
I had to do a few examples of what we did Monday with my other class. They needed some review, so let's do, this is perfect, because this is the kind of problem I like to give. So let's say that heights of kindergartners at a certain school are known to be normally distributed with a mean of 40 centimeters and a standard deviation of 3.5 centimeters. Okay, so everybody with me. That sounds like that's a standard kind of normal distribution problem. They give you mean, the standard deviation, right? And now I'm going to ask you a probability question. So one mistake students make is they think when we learn something new, all of a sudden everything's going to be that. But no. When is it that I have to change the standard deviation? Two things. I must take a sample, and I must ask a question about the sample mean. So have I taken a sample here? No. If I say pick one student, that still isn't a sample, is it? What's the probability that that student's height is more than 39 centimeters? That's a chapter 6 problem. What does that mean? That's a parking time problem, just like the last thing. Can you guys draw the picture and shade in the right place? Can you guys just do that and I'll catch up to you? If you weren't here Monday. So what goes in the middle?
40.
40. And of course, what data point are we interested in?
30.
39. And where do I shade? To the
I'll be to the right.
right. Yeah. So this is an arrow pointing you in the direction. So I learn all that. So already I know the answer is going to be more than 50%. That doesn't help with the specifics, but if I get 17%, I have done something wrong. I know that, right? Okay. What do I do now? I want to find the answer. And I've got a chart of all the answers. Yeah, so I have to make a z-score so that I can use the chart. How do I make a z-score?
Mean plus.
Yeah, so it's always our data point minus the mean divided by the spread. And whatever the hell that is. I think it's 0.2871?
2857.
29, okay. Negative 0.29. And again, there's a ton of little checks and balances. I already know the z-score is going to be negative, right? Because it's below the mean. So one of the most basic things students do is they flip this, but then you should know it's going to be negative. So if you don't get a negative, you go, okay, what the shit did I do, right? So a lot of little checks and balances. Now what do I do?
Look up the z-score for negative.
Yeah, look up negative 0.29.
0.3859.
So double check that. Not that I don't trust you, but I just want everybody to get that. Is that what you said, 3859?
Mm-hmm.
You guys agree? Do you concur? Okay. So is that the answer?
Nope.
Because we were nice to ourselves, right? We drew the picture, we shaded the thing, so I know when to stop. And I can't stop yet, because I ain't got this side. So what's this side?
1 minus.
Yeah, 1 minus that, so 6, 1, 4, 1. Now somebody help me out. What does that mean exactly?
That area is 0.6141 or 61.41% probability that the height is greater than 39 centimeters.
All right, so the probability that a kindergartner is taller than 39 centimeters is 61.41%. The other way to answer that question, so that's perfect, because that's a probability question. I picked one student, there you go. The other way to say that is 61.41% of all the kindergartners at the school are taller than 39 centimeters. Yes? Because, for example, if 10% of the people in this room are left-handed, and I pick one person, what's the probability I pick a left-handed person? 10% of everybody in this room is left-handed, let's pretend. I pick one person at random, what's the probability they're left-handed? 10%, right? Probability is percentage. So, and that's why. What are the chances I pick a left-handed person? Well, if 10% of the people are left-handed, there's a 10% chance I pick somebody. That's the probability, right? Okay, maybe. So that's why there's two kind of ways to look at this. Either as a probability or as a percentage. All right, so now let's bring in the new stuff. Bring in the new stuff. So now I'm going to pick a sample of students. Same stuff, we're still in problem number 1. Now we pick a random sample of 13 kindergartners. Blah, blah, blah. Just got tired in the middle of writing kindergarten. Yes?
What is the first thing say?
Pick. Okay. Immediately, what should I do? Oh, by the way, let me ask you a question. What's the probability that their sample mean is greater than 39 centimeters? Sample, did I say centimeters? Should be inches. That's very tiny people, by the way. I don't know if anybody was, sorry. You're like, it's like, what are you parents feeding you? Not much. All right, sorry. Nobody yelled at me. Anyway, sorry. All right, so 39 inches, that's much better. That's more there, so yeah, okay. What 2 things just happened that tells me exactly what to do? Did it take a sample? Yes. Am I asking a question about the sample mean?
Yes.
Yes. So what must I change? Your whole outlook, Jeff. Huh? No, the mean is one of the things that does not change. Standard deviation changes, right? So, this standard deviation I gave you works for individuals. That's exactly how we first calculated standard deviations, or how far away was each individual data point from the mean, yes? So the standard deviation we're given will almost always be the standard deviation for individuals. This problem is not talking about individuals, it's talking about groups of 13. I need the standard deviation for groups of 13. That's exactly what this does. This takes the old one and converts it into one for groups of 13. I really want that to make nothing but sense. Of course I can't use that for this problem. That's for individuals. I got 13 kids at a time. I need a different spread. Right? It's going to get skinnier, so it's going to be different. So what was it? 3.5 divided by what?
13.
Square root of 13. So one of the biggest mistakes is leaving out the poor little square root. By the way, this is one place, where variance actually kind of looks better. Do you see how it's just the new variance is the old variance divided by n? That's a little bit cleaner. But of course, when we take square roots, it becomes that. Okay. What the hell's that? What is 3.5 divided?
Standard deviation.
No, I mean, what is it? Sorry, what the number?
0.9707.
971? Is that right?
Yeah.
What's the line above the X for again?
Yeah, what's this mean?
The sample.
Sample mean. I like it. So what is this symbol? This is one symbol. Everybody listen. This is one symbol. This does not say sigma divided by x. This says sigma sub x bar. And you've seen subscripts before. Real quick. Anybody remember what this formula was for slope? I'll get it started. y2 minus y1 over x2 minus x1. Does that sound familiar? See little subscript dudes? Did that mean y divided by 2? Did that mean y times 2? No, that meant the second y, correct? And the first y, second x, and the first x. You with me?
Yeah.
So subscript just means I have a specific type of this. So that's a Y, but it's a specific one, the second Y. So everybody with me? This is a standard deviation, but it's a standard deviation of sample means. Kick ass. Yeah?
So for standard deviation, we round 3 places, not 4?
Yeah, at least 3. So if you do 4, little cheer. That's beautiful.
Oh.
But it's gotta be at least 3. Yeah. Okay. Okay. Now watch this. This is hilarious. 2.5 days we spent. We went to alternate universe, Florida. We did weird shit with blue and yellow and shit, you know. That is all. That is the only new thing. That is it. The rest of the problem works exactly the same way. What's it look like? Technically, it should be skinnier, but when you draw it, I don't care. You just draw it. You just need an anchor. It would be skinnier because there should be less chance for it to be extreme. It should all come in towards the middle. What's in the middle?
40.
40.
40 still. Mean stays the same. I'm still curious about 39. I still want to know the area above it. I still want to make a z-score. But now, when I do my data minus the middle, what do I divide by? 0.971, the correct spread. Here I divide it by 3.5, because that's how spread out individuals are. Here I better freaking divide by 0.971, because I'm talking about groups of 13. Do you guys see that? I really want you, do you see how all the work's the same? The picture's the same, everything's the same, except I just had to take a second and change the standard deviation. That's all that I'm adding in chapter 7. That's it. And sometimes I feel like somebody out there's gonna be like, all that shit about Florida and shit, and this is the shit. Can you just tell us this shit, Jeff? Shit. I'm like, I want you to buy in to why that makes sense, and I want it to make more sense what it represents. So what do I get here? Or what do you get there? I'm not doing it.
Negative 1.03.
1.03. All right, somebody help me out. When you look that up, what do you get? 0.15. 15? Neato. So then this would be
1 minus that.
0.8485.
good. Real quick. You guys are all with me when I say if I take samples, the picture gets skinnier than it used to be, yes? So here's what it looked like before, and there was 61.4% up there, yes? Now there's more, there's a bigger percent. Why? Because it gets skinnier. There's a lot less shit back here, there's a lot more shit over there. It goes towards the mean. Most samples should show up close to the actual average, right? If the average age of gross one is 25, and I go take a group of 80 people, what are you gonna put money on that the average is close to? 20-5, of course, because any sample I take, its mean should be close to the real mean, especially if it's a nice random sample. You with me? Very low chance I just happen to get a bunch of really young people or really old people, right? I should get a mixture. I should get close to the real mean. There's a chance I'll lose money, but it's a much higher chance I'm gonna make some money if I make that bet. Are you kind of with me? Okay. Okay. So that's all that's gonna happen. Let's do one more problem, then I always let you guys out early because for some reason, you guys don't ask as many questions, which I hope is a good sign. My other class, it takes a little longer, which is fine. I love questions. So if you guys have any questions, you gotta immediately ask me. Yes?
So we don't plug in the 13 at all in the graph.
The 13? Oh,
Yeah.
no.
Like at all.
Good point. So again, when I drew this, did we draw in the 3.5 anywhere? No. That went into what the shape was, right? So that 13 doesn't really show up here. It actually just goes into why it's skinnier because it's not as spread out. Okay. How's everybody else so far? Okay. Okay, let's do one more problem. Oh, and I still have to give you the practice test, don't let me forget. The average, I don't know, number of hot dogs eaten at contests is 17.418.
no idea where this topic came up from, but oh well.
Standard deviation, well, standard deviation is 5.162. Yeah.
I like it.
We take a sample of 47 hot dog contest contestants. Peeps. It says people on. Okay, is everybody with the idea? The average number of hot dogs eaten in contests amongst all people is 17.418. We randomly sample 47 hot dog contest participants. Are you with me? You with me? And I want to know what's the probability that the average they eat is less than 15 hot dogs. Do I say anywhere in that problem that it's normally distributed? So do you think we're justified to use the z-score chart?
No.
There is one saving grace. I don't say it's normal, but did I take a sample?
Yeah.
And how big is it?
47.
And that is bigger than 30. So chicken, lettuce, central limit theorem says all good. As long as the sample sizes we're taking are more than 30, when I plot the averages, I'm gonna end up with a normal enough curve. Do you understand how big that is? I've got a sheet. It's got all the freaking answers to any normal distribution problem in the universe. So if I know I'm working with a normal distribution, I'm allowed to just look up the answers, right? If I don't know, I need stats too, which we don't teach here, I'm sorry. Maybe someday. You guys kind of with me? With what we know, we couldn't do shit, right? They have to tell me it's normal or I can't do shit. Here it doesn't say it's normal, but it is normal. That means it's normal enough. When I say that, I mean normal enough for us to use the blue sheet of answers, right? Let me stop for a minute, yeah.
Homework would be a non-normal one?
They're, in a future section, they're a little loose, so I'm gonna make a comment about that. But in chapter 7, if I remember correctly, they're pretty good about, yeah. So if they didn't say it was normal and they only had a sample of 22, you can go ahead and say, I cannot do this problem, it is not normal, right? And a little tear comes out, because I always like to say the more you know, the less you should have to do, right? So I can't remember off the top, I'm pretty sure they're pretty good. In a future section, they do a couple things that are a little bit loose, and I'll tighten that up, okay. Is everybody okay with just the idea of what's happening here? So we can proceed. So this last problem, I was able to ask a question about one kid because I said at the beginning it was normally distributed, right? And nobody batted. By the way, I wanted to say something. Did I only pick 13? That's not bigger than 30. So why did we do this problem? Because it already was normal. I don't need a sample size of more than 30 to save my ass. It was already normal. Is this one normal? We have no freaking idea. We need a big enough sample size. We got it, sweet. And again, I think I said this earlier. If I take 47 hot dog contestants and I plot their number of hot dogs eaten, does that have to be normally distributed? Shit, no. If I take every sample of size 47 and plot all those averages, that's what's normally distributed. Okay, maybe. Okay, so now what do I do? Immediately, what should I do?
Plot it, graph it,
Plot it, graph it, twist it, bop it. What goes in the middle?
17.418,
Okay. And then what am I interested in?
15.
15, and I want less than 15. All right, so I accept that answer. Draw the picture is never a bad idea. What's the immediate thing I should do before I do any actual computations? No, before I do any computations,
Look up the Z.
find the new standard deviation. This one I gave you, this standard deviation, what's it for? Individuals. How do you know that? Because it doesn't have a little subscript on it. It doesn't say sigma x bar. So that is for individuals. Are we talking about individuals?
We're talking about means of 47 people. I need the standard deviation that works for that. Does that make? I really want you to look at this little formula. It takes the individual dude and it changes it into something that works for a sample size of n. That's what it does. Our poor little purple dude is dying. So what do we get? We get, what was it? 5.162 divided by what?
47.
Square root of 47. And then whatever this shit has. Let's see. I think it's, wait, what, don't say anything. It's gonna be 0.74. I don't know.
7.5.
Oh!
7.53.
It's not bad, right? Or is that not good enough? I'm sorry. Try again, Matt boy. Do it again, 753?
Yeah.
Okay. 7.4 is not good enough? Okay, it's fine. I just did 5.162 divided by square root of 47. Sorry, I'll stop. It's my one skill. I just, so now I can do what? Now I'm allowed to do what? Yeah, now I do all, so every step is the same. There's just this one little step we throw in there because we need the spread for groups, not the spread for individuals. That's it. Every freaking step other than that is the same. Find a z-score. Well, would it be what minus what?
15 minus 17.418.
Divided by
7.
the new spread, 11. Thirds, thirds 2.4.8, 3.2, negative 3 point, I don't know, 3 point, yeah, screw out, negative 3.2 or so. I don't know if I can trust my brain anymore. It's okay if I'm wrong. I'm a big enough man to take that. Anybody doing that?
I think I did it wrong. But
No, I could be totally wrong. So, 4/3. I think I'm right.
Negative 3.211.
Okay, come on. No, it's okay. Negative 3.21. Okay, I said negative 3.2. I'll stop. I'm sorry. It's all right. And then we look that up, right? You can get the area.
Yeah.
Is everybody with me? What do you get when you look up negative 321?
1,007.
Oh, 0.0007?
Yeah.
Okay. And of course, we don't have to do 1 minus because that's exactly the area I wanted, right? Whenever you look up a z-score on the chart, you immediately put it below what you looked up. That's the area below what you looked up. In this case, it's exactly what it asked for. Kick ass. Let me give you guys the practice test, which is up here somewhere. Oh my God. Hold on, guys. I got so much paper. So when you get the practice test, guys, number 5 is just like what we just did. Number 5 is your central limit theorem model. Oh, is there another paper? Okay. Monday review day on the answers for this, I'll have the quizzes graded. Don't forget your stuff, please.